Okay, so kinetic energy. Let's make a little XY plane here. This is going to be my Y direction, and this is going to be my X direction. Now, as we're looking at this XY plane, I don't want you to look at it as up and down. I want you to look at it the plane like the surface of your table. That's what we're looking at, is an XY plane. And we are going to take, let's just say we have a ball here. This ball, it's a closed system. I'm going to draw a system boundary around it. We're looking at this ball. Okay, and this ball is moving on the plane of that surface. Okay, now the path that it's following may be this path. This may be a path that it's following. So I'll write here path. And we have watched it as we're starting at, maybe this is my origin point 0, and we've moved this far, and I'm going to call this distance here distance S. We move this distance S. And it's going to move some distance ds as it keeps moving along. And to move this ball, maybe we've applied a force to it. So let me put a force here. What color should I use? I've used up all my good colors. Okay, well, let's do blue again. This is maybe my color. We're doing a force. That's a vector, but we're going to have some force here that's going to be tangential, and a force that's going to be normal. Okay, so we have a normal force that's perpendicular to the path, and a tangential force, or I'll call it the force in the S direction. Okay. Now here's the thing we know about this ball, or this particle, or whatever we're dealing with. It has some mass. It has mass, we're going to call that mass m. It has some velocity. We're going to call that velocity v. And it has some force, has a force acting on it. That force is F. Okay, now let's look at that. And we want to look at this ball as it moves from S1 or position 1 to position 2. Okay, so it's going to say, so we're going to say, let's look at this ball as it moves from state 1 to state 2. So we're going to have an S1 and an S2. We're moving from position S1 to position S2. And let's just say there's a velocity change. We're going to go velocity 1 to velocity 2. That's what we're going to do there. Now, gravity is also acting on this, but we're going to look at that separately. Okay, so we've purposefully done it on the plane of the table, so there's no potential energy effects here that we're going to be deriving here in a little bit. So we got to deal with the law that applies to this, and that's going to be Newton's second law. Newton's second law. Okay. Newton's second law states, as we know, the sum of all the forces is equal to the mass times the acceleration. It's a vector equation. But what I want to do is I don't want to look at it in the vector. I want to look at it only in the S direction, okay? The direction of our movement. That's what I want to do. Because the other direction isn't going to help us much, because remember, we're talking about this work. Work is force times the distance. It's going to be the force in the direction of our distance that we want to work with. So let's look at that in the S direction, or the tangential direction. Okay, so we're going to have the force in the S direction is going to be mass times, and acceleration is what we're going to be dealing with. Remember, acceleration is the change in velocity over the change in time. So we've rewritten acceleration because we're given the velocity. We're given the acceleration here. We're given the velocity, so this is what we're rewriting acceleration as. Now, what I want to do is I want to take advantage of the chain rule, by the chain rule. Now, you may hear something at home. My computer, I think I mentioned this before, my computer sometimes is processing these videos. The fans go on overdrive, so you may hear a little jet engine in the background. It's just my computer going, so sorry about that. I should move it far away, but I don't. By the chain rule, what we have here is we can write that the force in the S direction is equal to the mass times, we can say dV ds dt. Okay, that's a chain rule. That nothing's changed there. We're just expanding that equation. dv ds is telling us, if we say that in words, what does it mean in words? It's better to say things in words and look at an equation. This is saying the change in velocity over the change in distance. Okay. The second term here, ds dt, is the change in position over the change in time. If you look at that units, position over time, that's going to give you, this is just going to give you velocity. Okay, so this is another way to write this equation. And so that's what we're going to do. We're going to write it that way. We're going to say Fs is equal to mass times the velocity times dv ds. Now, what I'm going to do now is I'm going to separate variables. I'm going to move ds to the left-hand side of the equation. So I'm going to say moving ds to the left-hand side, LHS. Also my high school, Lake and Bronx. If you want me to, I can sing the school song. I'll sing it later. I'll let that be a little bit, you can wait. In this lecture, I will sing the Lake and High School school song, which was written by my great aunt. That's another fun fact that you don't care anything about, but that fact is true no matter what. Okay, so here we go. Fs ds is equal to mv. Okay, now we want to get rid of all this stuff. Oh, I forgot dv. You're yelling at me. mv dv. Okay. Now we want to integrate that because we want to get rid of all these dv's, and so let's integrate between the limits that we set earlier on. So my limits here that I said, we're going to do from S1 to S2 of Fs ds, and the other side we're going to go from V1 to V2 of mv dv. Okay. Now, let's look at the right-hand side. The right-hand side. So looking at the right-hand side, RHS. I didn't go to a school with the initials RHS. So RHS. V1 to V2, I almost wrote a volume there because I'm so used to writing volumes. V1 to V2 is equal to mv dv. Okay, now, rules of integrals. Here, we can do this, should be able to do this integral very easily. Mass is constant. It's not changing because it's a closed system, so that can come outside of the integral. So we now have the integral of v dv. The integral of v dv should be one of those integrals that you can do in your head. So this is going to be 1/2 mass times v squared, and we're going to integrate that between v1 and v2, or evaluate it between v1 and v2. So we're going to get 1/2 mass times v2 minus v1. Both these things are squared. Okay, what is that? That's kinetic energy right there. 1/2 mv squared is kinetic energy. You know that. You're familiar with that. This is old stuff. We're going to write that in this class in several ways. We can say delta Ke is equal to, maybe we can say the kinetic energy at state 2 minus the kinetic energy at state 1. We always do final minus initial. Or we can write that as 1/2 m times v2 squared minus v1 squared. I might write it as any of these forms this semester. They're all applicable. Every one of them can do the same thing. Okay. Now my question for you, and this is the question that is going to be the top, not the top hat question, the lecture question today. The lecture question for today is kinetic energy a property? Is kinetic energy a property? Okay, is kinetic energy a property? Now remember, properties do not need to know if you're going the path that you take from state 1 to state 2. It just needs to know about state 1 and state 2. Okay, that should be enough information right there to remind you, is kinetic energy a property? That's what you need to figure out. Okay. Now, let's look at the left-hand side. Oh, that's LHS again. Okay, here we go. To Lake and High we sing, let our praises be told. We love our colors royal, the purple and the gold. To her we will always be. To her we will loyal be. I don't remember. In victory or defeat, yes, we will cheer for Lakin, the team that can't be beat. What did I? To her we will loyal be. I let you down. I can't believe that I, a proud Lakin High School alum, flubbed the Lakin High School song. I'm going to have to get this ready, and maybe in the next segment I will get it right. I'm disappointed in myself. You should call. I'm probably going to revoke my high school diploma if they watch this video. Anyway, you're saying just get done with this lecture, Wanklin. I have time. I have other things I need to do. I don't want to listen to you sing on lecture. Too bad. I'm sorry. This is what you paid good money for, is my vocal stylings about songs I don't remember. Okay. This equation here, when we look at this, we're taking force times distance. This is going to give us work. Okay, so the left-hand side of our equation is work. Okay, this is work transferred to the body from the force. Okay, now let's look at our units here. The units here, work, is going to be, the force is going to be newtons, the distance is going to be meters in SI. Okay, and that's what we're going to call a newton times a meter is going to be a joule. Okay, well, we're just going to say this is equal to a capital J. Okay, that's an SI. Now, in English units, English engineering units, our force is going to be in pounds force. Our distance is going to be in feet. Okay? Now, in SI units, we're not going to be able to, or sorry, in English units, we're not going to just be that simple. What we're going to have to do is we're going to have to convert this. We are going to convert pounds force feet, and we're going to say that 778 pounds force feet is in 1 BTU. And that is going to be, we're going to put our answers in BTUs. Complicated. Always have to go convert from pounds force feet. You're going to have to do a conversion to get it to BTU every time. Every time. Okay? Now, you might be looking at that and you say, well, in this equation, the left-hand side and the right-hand side of the equation must have the same units. Must have the same units. So what are our units of kinetic energy? They have to be either joules or BTUs. So let's look at this. 1/2 mv squared. What are the units? In SI, we have 1/2 has no units. Mass is in kilograms. Velocity is in meters per second, but we're going to square that, so meters squared per second squared. Okay, so I look here and I say, well, my conversion is going to be that 1 Newton is 1 kilogram meter per second squared. Okay, that's a known thing. 1 Newton is 1 kilogram meter per second squared. Look here, kilograms cancel, one of the meters cancel, both the seconds cancel, and I get Newton meters. I get Newton meters, so this is equal to Newton times a meter, which is equal to a joule. Okay, great. Great. Think it's going to be that easy in English engineering units? No, not at all. Not at all. Not at all. So English engineering units. We have 1/2 has no units. Mass has a unit of a pound mass. Velocity has units of feet per second squared. Feet per second. So, sorry, feet per second. We're going to square that and have feet per second squared. Feet squared per second squared. Now remember, look up here. We want to get it somewhere where it has pounds force. So we're going to have to convert pounds mass to pounds force. And you just can't say 1 pound mass is equal to 1 pound force. No, 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 no. We have to do the conversion. And so we're going to say 32.2 pound mass feet per second squared is in 1 pound force. Okay, then let's see what we get. We do that. Pound mass cancels. One of our feet cancels. Seconds cancel. And now we have pounds force feet. And now we can do the conversion. 778 pounds force feet is in 1 BTU. Okay, to get ourselves to BTUs. Okay, this sucker right here, remember it, it's going to come after you. You can do the calculation correct. What I see students all the time is that they plug into this equation, they're done with the calculation, they end. That's wrong. You have to do the conversion. You have to do the conversion so that you can make sure that you're okay. Okay. When a body is accelerated by a force, work can be considered as a transfer of energy to that body where it is stored in kinetic energy. Okay? Work is transferred to the body, stored as kinetic energy. That is our information about kinetic energy today. We'll go on to potential energy after this.